Decarburization damage mechanisms as a part high-temperature corrosion greater than 400 degrees Fahrenheit or 204 degrees Celsius. Description of decarburization damage based on API 571. Carbon is absorbed into a material at elevated temperature while in contact with a carbonaceous material or carboizing environment. Decarburization damage, an in-depth explanation. Introduction. Decarburization is a microstructural phenomenon in ferrous alloys, particularly steels and cast irons, where surface carbon content is reduced due to chemical reactions with the surrounding environment at elevated temperatures. This process results in the loss of carbon from the steel's surface layers, leading to significant changes in material properties such as hardness, strength, and toughness. Decarburization is a common concern in high-temperature applications like heat treatment, welding, forging, and service in oxidizing or carboizing environments. Understanding decarburization. Decarburization damage refers to the deterioration of ferrous alloy surfaces caused by the loss of carbon from the microstructure during high-temperature exposure. This process results in a characteristic microstructural alteration near the surface, which significantly impacts the material's mechanical properties and performance. Microstructurally, decarburization manifests as a distinct zone beneath the surface where the original microstructure, such as perlite, cementite, or other carbides, has been depleted of carbon. This zone, known as the decarburized layer, is typically softer and weaker than the unaffected core material. The depth of this layer depends on factors such as temperature, exposure duration, atmosphere composition, and alloy composition. In the decarburized region, the microstructure predominantly consists of ferrite, a softer, less hard phase, due to the removal of cementite, Fe3C, which is responsible for the high hardness and strength in steels. The transition from the decarburized zone to the unaffected core often exhibits a gradual microstructural change, with a zone of partial decarburization in between. This damage is often characterized by surface discoloration, such as a bluish or brownish hue, resulting from oxidation accompanying decarburization. Over time, the softened surface becomes more prone to wear, microcracking, and fatigue failure, especially under cyclic loading conditions. Overall, decarburization damage leads to a loss of surface hardness, reduction in tensile strength, and increased susceptibility to corrosion or fracture, compromising the integrity and lifespan of metallic components used in high-temperature environments. Decarburization occurs when the surface of a steel component reacts with oxygen, water vapor, or other oxidizing agents at elevated temperatures, causing carbon atoms to diffuse out of the metal lattice. The primary chemical reaction can be summarized as Fe3C3-4 of O2 became 3Fe-CO or CO2. This process results in a depletion zone near the surface where the carbon concentration falls below the threshold required for maintaining certain microstructures, like perlite or cementite. Mechanism of decarburization. Number 1. High-temperature exposure. When steel is heated to temperatures typically above 600 degrees Celsius or 1112 degrees Fahrenheit, especially in oxidizing environments, decarburization can occur rapidly. Number 2. Surface reaction. Carbon in the steel reacts with oxygen or other oxidizing gases, forming gaseous carbon oxides, CO, CO2. Number 3. Diffusion of carbon. As the surface carbon reacts and leaves, a concentration gradient forms, causing carbon atoms from the interior to diffuse outward to re-establish equilibrium. Number 4. Formation of depletion zone. Over time, a zone with significantly reduced carbon content develops near the surface. This is the decarburized layer. And number 5, microstructural changes. The decarburized zone often transforms from the original microstructure such as perlite and cementite into softer phases like ferrite or even pure iron, leading to a reduction in hardness and strength. Microstructural features of decarburization. Number 1, depletion layer, a surface zone with reduced or absent cementite and perlite, composed mostly of soft ferrite or austenite if heated in austenitizing conditions. Number 2, transition zone, gradual interface between decarburized and unaffected regions. Microstructure gradually changes, often leading to microcracks due to differential properties. And number 3, depth of decarburization, depending on temperature, time, atmosphere, and alloy composition. The decarburized layer can be shallow, a few micrometers, or deep millimeters. Effects of decarburization on material properties. Number 1. Reduced hardness. Loss of carbon weakens the microstructure, making the surface softer. Number 2. Lower wear resistance. Softer surface layers are more susceptible to abrasive and adhesive wear. Number 3. Decreased fatigue life. The softer decarburized layer is more prone to crack initiation under cyclic stresses. Number 4. Increased susceptibility to corrosion. The decarburized surface is more reactive and less corrosion resistant. Number 5. Loss of mechanical integrity. Overall strength, toughness, and load-bearing capacity are compromised, especially critical in load-bearing parts. Common industries and components affected. Number 1. Power plants, turbine blades, boiler tubes, and headers operating in oxidizing atmospheres. Number 2. Automotive, crankshafts, camshafts, and gears exposed to high-temperature environments. Number 3. Aerospace, turbine engine components subjected to high temperatures. Number 4. Manufacturing and heat treatment, components subjected to improper furnace atmospheres during hardening or annealing processes. Preventing and controlling decarburization. Number 1. Use of protective atmospheres. Conduct heat treatments in inert or reducing atmospheres, e.g., nitrogen, argon, or endothermic gases, to minimize oxidation. Number 2. Surface coatings. Apply coatings such as aluminide or chromide layers that serve as barriers against oxygen ingress. Number 3. Proper heat treatment procedures. Control temperature, duration, and atmosphere during heat treatment to limit decarburization depth. Number 4. Post-treatment surface treatments, recarburization or surface hardening to restore surface properties if decarburization occurs. Inspection and detection of decarburization. Number 1. Visual inspection. Discoloration or surface oxidation may indicate decarburization. Number 2. Microstructural analysis. Metallography with polishing and etching reveals the decarburized zone. Number 3. Hardness testing. Microhardness measurements across the surface depth can identify softer decarburized layers. Number 4. Chemical analysis. Techniques like electron probe microanalysis, EPMA, or energy dispersive X-ray spectroscopy, EDS, measure carbon content profiles. Number 5. Non-destructive testing. Ultrasonic or magnetic methods can sometimes detect the decarburized zone if it causes significant microstructural changes. Description summary of decarburization damage. Decarburization damage occurs when the surface layer of steel loses carbon due to high-temperature oxidation or reactions with gases, leading to microstructural transformation, reduced hardness, and compromised mechanical properties. It is a prevalent issue in high-temperature service environments and heat treatment processes. Effective control measures include atmosphere regulation during heat treatment, protective coatings, and routine inspection methods to detect early signs of decarburization. Decarburization damage affected materials based on API 571 is carbon steels and low alloy steels. Materials affected by decarburization damage. Decarburization primarily affects ferrous alloys, especially steels and cast irons, which contain significant amounts of carbon within their microstructure. The extent and severity of decarburization depend on the alloy composition, microstructure, and environmental conditions during high-temperature exposure. Number 1 of the materials affected by decarburization damage is carbon steels. Carbon steels are the most commonly affected materials. These steels have varying carbon contents, typically ranging from low, 0.05%, to high, up to 1%, and are used extensively in structural and mechanical components. Medium and high carbon steels are particularly vulnerable because their microstructure relies heavily on cementite and perlite for hardness and strength. Decarburization causes a depletion of cementite near the surface, resulting in softer, less durable layers. Low-carbon steels may also experience decarburization, especially in high-temperature environments, leading to reduced surface hardness and wear resistance. Number 2 of the materials affected by decarburization damage is alloy steels. Alloy steels contain additional elements such as chromium, nickel, molybdenum, and manganese, which can influence their resistance to decarburization. Despite their improved corrosion and oxidation resistance, many alloy steels still suffer from decarburization if not properly protected during high-temperature processes. For example, chromium alloyed steels used in turbine blades or pressure vessels are susceptible especially if the protective atmosphere is compromised. Number 3 of materials affected by decarburization damage is cast irons. Gray cast iron and other cast iron varieties can also be affected, particularly if they have a significant carbon content in their microstructure. Decarburization can alter their surface microstructure, reducing hardness and wear resistance, which is critical in applications such as engine blocks and machinery parts. Number 4 of materials affected by decarburization damage is special steels and high-temperature materials. Tool steels, martensitic steels, and stainless steels are susceptible if exposed to oxidizing environments at high temperatures. Stainless steels with chromium content such as 304 and 316 are somewhat resistant but still prone to decarburization if the environment is highly oxidizing or if the material is heated excessively without protective atmospheres. Number 5 of materials affected by decarburization damage is coated and surface-modified materials. Materials coated with protective layers such as ceramic coatings and aluminides may still experience decarburization if the coating fails or is compromised, exposing the underlying steel to oxidizing atmospheres. Factors influencing material susceptibility. Number 1, carbon content. Higher carbon content in the alloy increases potential for decarburization, as more carbon is available to diffuse out. Number 2, alloy composition. Elements like chromium, nickel, and molybdenum can enhance resistance but do not eliminate susceptibility. Number 3, microstructure. Microstructures rich in cementite or other carbides are more prone to decarburization. Number 4, environmental conditions, presence of oxygen. Water vapor, or other oxidizing gases at elevated temperatures accelerates decarburization. And number 5, temperature and duration. Higher temperatures and longer exposure times promote deeper and more extensive decarburization. Summary of decarburization damages affected materials. Decarburization damages a broad range of ferrous materials, especially various types of steels, carbon steels, alloy steels, and cast irons, by causing surface microstructural degradation. The susceptibility depends on alloy composition, microstructure, environmental conditions, and operational parameters. Proper protective measures and material selection are essential to minimize decarburization in high-temperature applications. Decarburization damage critical factors based on API 571, Number A, time, temperature and carbon activity of the process stream are the critical factors. Number B, the material must be exposed to a gas phase that has a low carbon activity so that carbon in the steel will diffuse to the surface to react with gas phase constituents. Number C, the extent and depth of decarburization is a function of the temperature and exposure time. Number D, typically, shallow decarburization can slightly decrease the strength of the material, but has no detrimental effect on the overall performance of the component. However, it is indicative that the steel may have been overheated and suggests other effects may be present, e.g. decarburization associated with HTHA in hydrogen services. And number 5, potential loss in room temperature tensile strength and creep strength may occur. Critical factors influencing decarburization damage. Decarburization is a complex process influenced by multiple interrelated factors that determine the extent, depth, and severity of the damage. Understanding these factors is essential for predicting, preventing, or controlling decarburization in high-temperature environments. Number 1 of the critical factors influencing decarburization damage is temperature of exposure. Key role, temperature is the most influential factor affecting decarburization. Details, elevated temperatures accelerate the diffusion of carbon atoms from the steel surface into the environment. Typically, decarburization becomes significant at temperatures above 600 degrees Celsius or 1112 degrees Fahrenheit, with the rate increasing exponentially with temperature. At very high temperatures above 900 degrees Celsius, the process can occur rapidly, causing deep decarburized layers in a short period. The Arrhenius equation describes the temperature dependence of diffusion rates, indicating that small increases in temperature can lead to large increases in decarburization rate. Number 2 of the critical factors influencing decarburization damage is exposure duration. Key role, the length of time the material is exposed to high-temperature oxidizing environments directly influences the depth and severity of decarburization. Details, longer exposure times allow more carbon to diffuse out of the microstructure, even at moderate temperatures. Prolonged exposure can lead to significant decarburization. The relationship between time and decarburization depth is typically nonlinear. Initial stages progress slowly, then accelerate with time. Number 3 of the critical factors influencing decarburization damage is atmosphere composition. Key role: the chemical environment surrounding the material determines the oxidation-reduction reactions at the surface. Details: oxidizing atmospheres rich in oxygen, air, steam, or oxidizing gases promote decarburization. Reducing or inert atmospheres, e.g., nitrogen, argon, can significantly reduce or prevent decarburization. Presence of water vapor or other reactive gases enhances oxidation and accelerates carbon loss. The partial pressure of oxygen is critical. Higher oxygen partial pressure increases decarburization rate. Number 4 of the critical factors influencing decarburization damage is microstructure and carbon content. Key role: the initial microstructure and carbon distribution influence how susceptible a material is. Details: microstructures rich in cementite, Fe3C, or other carbides are more prone to decarburization because these carbides are sources of carbon. Steels with higher carbon content have more carbon available to diffuse out, increasing vulnerability. Microstructural features such as grain size, prior heat treatment, and phase distribution affect diffusion pathways. Number 5 of the critical factors influencing decarburization damage is alloy composition. Key role: alloying elements can either inhibit or promote decarburization. Details: elements like chromium, nickel, molybdenum, and vanadium can form stable carbides, reducing free carbon available for diffusion. Chromium can form a protective oxide layer that acts as a barrier to decarburization. Conversely, some alloying elements may catalyze oxidation or influence diffusion rates. Number 6 of the critical factors influencing decarburization damage is surface condition and coatings. Key role: surface finish and protective coatings impact the rate of decarburization. Details: rough or damaged surfaces may have increased oxidation rates. Protective coatings, e.g., ceramic, aluminide, can serve as barriers to oxygen diffusion, reducing decarburization. Coating integrity is critical. Any breach exposes the substrate to oxidizing agents. Number 7 of the critical factors influencing decarburization damage is heat treatment and manufacturing processes. Key role: the prior thermal history influences microstructure stability and decarburization susceptibility. Details: heat treatments that produce high carbon microstructures increase susceptibility. Processes such as welding, annealing, or forging at high temperatures can modify microstructure and residual stresses, affecting decarburization behavior. Number 8 of critical factors influencing decarburization damage is mechanical stresses. This is the key role. Mechanical stresses can influence diffusion and damage progression, and these are the details. Tensile stresses may accelerate microcrack formation in decarburized zones. Fatigue loading can exacerbate damage in the softened decarburized surface layer. Decarburization damage affected units or equipment based on API 571. Number A, decarburization can occur in almost any equipment that is exposed to elevated temperatures, heat-treated or exposed to a fire. And number B, piping and equipment in hot hydrogen service in hydroprocessing units or catalytic reforming units as well as fired heater tubes can be affected. Pressure vessel components that are hot formed during fabrication can be affected. Units and equipment susceptible and/or affected to decarburization damage. Decarburization primarily impacts ferrous components used in high-temperature environments. The extent of damage and failure depends on the operational conditions, material selection, and protective measures. Number 1 of units and equipment susceptible and/or affected to decarburization damage is power plant components. Number A, boilers and heat exchangers. Description: components operate at high temperatures to generate steam. Impact of decarburization: surface softening reduces thermal fatigue resistance. Decreased hardness leads to increased wear, erosion, and corrosion. Microstructural degradation causes premature failure of boiler tubes and headers. Number B, of the power plant components is turbine blades and casings. Description: critical parts in thermal power plants. Impact of decarburization: decarburization weakens blade surfaces, leading to crack initiation. Reduced surface hardness lowers erosion and corrosion resistance. Number C, of the power plant components is superheaters and economizers. Impact of decarburization, microstructure deterioration compromises heat transfer efficiency and structural integrity. Number 2 of units and equipment susceptible and or affected to decarburization damage is chemical and petrochemical equipment. Number A, reactor vessels and shells. Description: operate at elevated temperatures and sometimes corrosive environments. Impact of decarburization: decarburized layers can cause surface cracking and structural weakening. Number C, of the chemical and petrochemical equipment is heat treatment furnaces and quenching tanks. Impact of decarburization: decarburization during high-temperature operation reduces the hardness of furnace parts, affecting process accuracy and safety. And number D, of the chemical and petrochemical equipment is distillation columns and piping. Impact of decarburization: degraded surface integrity can lead to leaks or failures under pressure. Number 3 of the units and equipment susceptible and or affected to decarburization damage is metallurgical and manufacturing equipment. Number A, rolling mills and steelmaking equipment. Description: processes involving high-temperature steel handling. Impact of decarburization: surface decarburization reduces the wear resistance of rolls, impacting product quality. Number B, of the metallurgical and manufacturing equipment is heat treatment furnaces and quenching equipment. Impact of decarburization: decarburization of tooling and fixtures leads to reduced lifespan and performance. And number C, casting molds and dies. Impact of decarburization: surface degradation affects precision and lifespan. Number 4 of the units and equipment susceptible and or affected to decarburization damage is aerospace components. Number A, gas turbine components such as blades, discs and casings. Impact of decarburization: surface decarburization reduces fatigue life, increases crack initiation, and decreases overall durability. Number B, landing gear and structural parts. Impact of decarburization: microstructural weakening can lead to failure under cyclic stresses. Number 5 of the units and equipment susceptible and or affected to decarburization damage is automotive components. Number A, engine valves and pistons. Impact of decarburization: decarburization leads to surface softening, increased wear, and potential failure. Number B, exhaust manifolds and turbochargers. Impact of decarburization: reduced hardness makes these parts more susceptible to thermal fatigue and corrosion. Number 6 of the units and equipment susceptible and or affected to decarburization damage is nuclear reactor components. Number A, reactor pressure vessels and core components. Impact of decarburization: surface degradation can compromise containment integrity and safety margins. Number 7 of the units and equipment susceptible and or affected to decarburization damage is marine and offshore equipment. Number A, propellers, shafts, and turbines. Impact of decarburization: decarburized surfaces are prone to corrosion, erosion, and fatigue failure in harsh marine environments. Number B, offshore platform structures. Impact of decarburization: surface weakening can lead to structural failures under cyclic loads. Number 8 of the units and equipment susceptible and or affected to decarburization damage is industrial furnaces and kilns. Number A, refractory lined equipment. Impact of decarburization: decarburization of steel parts near high-temperature zones reduces lifespan and increases maintenance. Summary table of decarburization damage mechanisms affected units or equipment. For the power plant boilers described as steam generation, decarburization effects are surface softening, cracking, and reduced durability. For the turbines, gas steam, described as power generation, decarburization effects are microstructural weakening and crack initiation. For the chemical reactors described as high-temp processing, decarburization effects are surface degradation and cracking. For the steel rolling mills described as metal forming, decarburization effects are reduced wear resistance and surface deterioration. For the aerospace turbomachinery described as aircraft engines, decarburization effects are fatigue failure and crack formation. For the automotive engine parts described as vehicles, decarburization effects are wear and reduced strength. For the marine propulsion systems described as ships, decarburization effects are corrosion, fatigue and failure risk. And for the nuclear reactor components described as energy, decarburization effects are safety-critical surface degradation. Conclusion of decarburization damage affected units or equipment. Decarburization can affect a wide range of high-temperature equipment across industries. It primarily weakens the surface microstructure of ferrous components, leading to reduced hardness, increased susceptibility to cracking, wear, corrosion, and ultimately, failure of critical equipment. Preventive measures include protective atmospheres, coatings, controlled heat treatments, and regular inspection to mitigate decarburization-related issues. Appearance or morphology of decarburization damage based on API 571, Number A, damage can be verified by metallography. Number B, damage occurs on the surface exposed to the gas environment but in extreme cases may be through wall. Number C, the decarburized layer will be free of carbide phases. Carbon steel will be pure iron. See Figure 4-123 typical low-carbon steel microstructure showing ferrite phase, light grains, and perlite carbide, dark layered phases. See Figure 4-124 microstructure illustrating a decarburized low-carbon steel where the strength-providing perlitic phases have been decomposed as a result of the removal of carbon atoms by diffusion to the surface. Morphology and appearance of decarburization damage. Decarburization manifests as distinctive surface and subsurface microstructural features that can be observed through visual inspection, metallography, or microscopic analysis. Its morphology depends on the severity, temperature, exposure time, and material properties. Below is an in-depth description of typical features and their characteristics. Number 1 of the morphology and appearance of decarburization damage is surface appearance. Number A, color changes. Sometimes, decarburized regions may show a dull, matte, or discolored surface compared to the unaffected areas. The formation of oxide layers or scale may impart a bluish, brown, or black hue depending on oxidation products. Number B of the surface appearance is surface texture. The affected area often appears roughened or pitted due to the loss of carbon and microstructural integrity. The surface may exhibit microcracks or irregularities resulting from weakening of the microstructure. Number C of the surface appearance is loss of shine or gloss. Decarburized zones are usually less shiny because of surface oxidation and microstructural changes. Number 2 of morphology and appearance of decarburization damage is microstructural features. Number A, reduced or absent cementite, Fe3C, in steels with perlitic microstructures. Decarburization results in loss of cementite at the surface. This leads to ferrite-rich zones with finer grains or coarse grain boundaries depending on the microstructure. Number B of microstructural features is formation of decarburized layer, a diffusion zone characterized by ferrite, alpha iron, with very low carbon content. The decarburized layer is typically harder and softer than the core, depending on the microstructure. Number C of microstructural features is gradient zone. A transitional zone exists between the unaffected core and the fully decarburized surface. It exhibits a gradual decrease in carbon content, which can be observed as a diffusion gradient. Number D of microstructural features is microcracks and pitting. The weakened surface is more prone to microcracking, especially under stress. Microcracks may appear perpendicular or parallel to the surface. Number 3 of the morphology and appearance of decarburization damage is cross-sectional morphology. Number A, decarburized layer thickness, varies depending on exposure conditions, can range from micrometers to millimeters. The layer appears as a distinct zone with a less dense microstructure. Number B of cross-sectional morphology is layered structure, typically shows 3 zones: outer decarburized layer, low carbon, ferrite-rich, transition zone, gradual change in carbon content, undisturbed core, original microstructure with higher carbon content. And number C of cross-sectional morphology is porosity and scale. Oxidation products may form scale or voids within or on the surface, especially if oxidation is severe. Number 4 of the morphology and appearance of decarburization damage is fractography and damage patterns. Number A, cracks and fracture surfaces. Decarburization surfaces often show intergranular cracks or transgranular cracks. Fracture surfaces tend to be dull, rough, and lacking metallic luster. Number B, brittle features. The decarburized zone is often brittle, leading to quasi-cleavage or intergranular fracture patterns. Visual and metallographic indicators of the appearance and morphology of decarburization damage. If feature of the appearance and morphology of decarburization damage is color changes, that described as dull or discolored surface, then the significance would be indicates oxidation and decarburization zones. If feature of the appearance and morphology of decarburization damage is surface roughness, that described as rough, pitted, or flaky surface, then the significance would be microstructural weakening. If feature of the appearance and morphology of decarburization damage is layered microstructure, that described as clear zone of low-carbon ferrite beneath unaffected core, then the significance would be decarburized layer. If feature of the appearance and morphology of decarburization damage is microcracks, that described as fine cracks on the surface or subsurface, then the significance would be microstructural weakening and stress concentration. If feature of the appearance and morphology of decarburization damage is loss of cementite, that described as absence of carbide particles in decarburized zone, then the significance would be carbon depletion. Summary of appearance and morphology of decarburization damage. The first is visual appearance, often shows dull, matte, or discolored surface, may have roughened texture, microcracks, or scale. The second is microstructural morphology, characterized by a ferritic microstructure with reduced or absent cementite, shows a gradient zone between decarburized surface and unaffected core. And the third is fracture and damage patterns. Cracks tend to be intergranular or transgranular. The zone is often brittle and prone to failure. Conclusion of the appearance or morphology of damage. Decarburization damage exhibits a characteristic morphology that includes a visibly altered surface, a distinct low-carbon decarburized layer, and microstructural features such as loss of cementite, microcracks, and increased brittleness. Recognizing these features through visual inspection, metallography, and microscopy is critical for assessing damage severity and determining necessary remedial actions. Decarburization damage prevention and mitigation based on API 571, Number A, decarburization can be controlled by controlling the chemistry of the gas phase and alloy selection, API RP 941. Number B, alloy steels with chromium and molybdenum form more stable carbides and are more resistant to decarburization. And number C, steels operating in high-temperature hydrogen environments should be selected in accordance with API RP 941. Prevention and mitigation strategies of decarburization damage. Decarburization is a microstructural phenomenon primarily caused by high-temperature exposure in oxidizing environments, leading to carbon loss from the steel surface. Effective prevention and mitigation require controlling environmental, operational, and material factors. Below are detailed strategies. Number 1 of the prevention and mitigation strategies of decarburization damage is control of atmosphere during heat treatment and operation. Number A, use of protective atmospheres, employ inert or reducing atmospheres such as argon, nitrogen, endothermic gases, or vacuum in furnaces to prevent oxidation and decarburization. Gas purity. Ensure high-purity gases to avoid contamination that promotes oxidation. Number B, covering or encapsulation. Use protective coatings or coverings such as slag, fluxes, or ceramic coatings during high-temperature processes to isolate steel surfaces from oxidizing agents. Number B, inert gas purge. Continuously purge furnaces with inert gases to maintain a reducing environment. Number 2 of the prevention and mitigation strategies of decarburization damage is material selection and heat treatment practices. Number A, use of decarburization-resistant materials. Select alloys with lower susceptibility to decarburization, such as highly alloyed steels with elements like chromium, nickel, or molybdenum, which improve oxidation resistance. Number B, controlled heat treatment parameters. Limit exposure time at high temperatures. Use the lowest effective temperature for heat treatments. Implement rapid heating and cooling cycles to minimize the duration of high-temperature exposure. Number 3 of the prevention and mitigation strategies of decarburization damage is surface protection techniques. Numera, coatings. Apply protective coatings such as nickel plating, carbide coatings, ceramic or refractory coatings to act as barriers against oxygen ingress. Number B, paints and sealants. Use high-temperature paints or sealants designed to resist oxidation and decarburization. Number C, metallic cladding or overlay. Overlay susceptible steels with corrosion-resistant materials to shield the surface. Number 4 of the prevention and mitigation strategies of decarburization damage is process design and operational controls. Number A, controlled heating and cooling. Use controlled ramp rates to avoid rapid oxidation, limit dwell times at high temperatures. Number B, atmosphere monitoring. Continuously monitor furnace atmospheres for oxygen and carbon potential. Adjust gas compositions dynamically to maintain optimal conditions. Number C, avoiding oxygen-rich environments. Minimize exposure to air or oxygen-rich atmospheres during high-temperature operations. Number 5 of the prevention and mitigation strategies of decarburization damage is post-processing treatments. Number A, carburizing or recarburizing. For components that may have lost surface carbon, controlled carburization can restore decarburized surfaces. Number B, surface hardening. Use induction hardening or flame hardening in unaffected areas to improve surface strength. Number 6 of the prevention and mitigation strategies of decarburization damage is inspection and monitoring. Number A, regular inspection. Use visual inspection, metallography, or non-destructive testing or NDT methods such as ultrasonic, magnetic particle testing to detect early signs of decarburization. Number B, microstructure analysis. Conduct microstructural examinations periodically to assess the depth of decarburization. Number C, sample testing. Use carbon content analysis at the surface and subsurface layers to monitor decarburization levels. Number 7 of the prevention and mitigation strategies of decarburization damage is design considerations. Number A, component geometry. Design components with thicker surfaces or buffer zones to withstand decarburization effects. Number B, operational environment design. Design equipment and processes to operate in environments with minimal oxygen exposure. Summary of decarburization damage prevention and mitigation strategies. If the prevention and mitigation strategies in use is use of protective atmospheres, that described as inert or reducing gases in furnaces, it is purpose to prevent oxidation and decarburization during heat treatment. If the prevention and mitigation strategies in use is material selection, that described as high alloy steels with oxidation resistance, it is purpose to reduce susceptibility to decarburization. If the prevention and mitigation strategies in use is protective coatings, that described as nickel plating, ceramic coatings, it is purpose to barrier against oxygen ingress. If the prevention and mitigation strategies in use is controlled heating cooling, that described as rapid temperature changes, limit high temp duration, it is purpose to minimize exposure time at high temperature. If the prevention and mitigation strategies in use is surface treatments, that described as carburizing, surface hardening, it is purpose to restore or enhance surface properties. If the prevention and mitigation strategies in use is regular inspection, that described as microstructure analysis, NDT, it is purpose to detect early signs and prevent failure. If the prevention and mitigation strategies in use is equipment design, that described as thick walls, protective features, it is purpose to reduce impact of decarburization on critical parts. Conclusion of the decarburization damage prevention and mitigation. Preventing or mitigating decarburization damage involves a combination of environmental control, material selection, protective coatings, process management, and regular inspection. Implementing these strategies helps maintain the microstructural integrity of steel components, ensuring their durability, performance, and safety over their service life. Decarburization damage inspection and monitoring based on API 571. Number A, field metallography and replication or FMR can confirm decarburization. Number B, decarburization results in a softening that can be confirmed by hardness testing. Certainly. Here's a detailed overview of inspection and monitoring methods used to detect decarburization damage. Inspection and monitoring methods for detecting decarburization damage. Decarburization can significantly weaken steel components, so early detection is crucial. The methods employed combine visual, microstructural, chemical, and non-destructive evaluation techniques. Below is an in-depth discussion of these methods. Inspection and monitoring methods for detecting decarburization damage. Number 1, visual inspection. It is purpose to, initial assessment to identify surface anomalies indicative of decarburization. Procedure of visual inspection is to, examine the surface under good lighting conditions, look for color changes, roughness, pitting, scaling, or discoloration. Note areas with dull, matte, or oxidized appearance. Visual inspection limitations. Surface inspection may not reveal subsurface decarburization, requires experience to distinguish from other surface defects. Number 2 of the inspection and monitoring methods for detecting decarburization damage is microstructural examination or metallography. It is purpose to observe the microstructure and measure the decarburized layer's depth. Procedure of microstructural examination or metallography is to cut a cross-sectional specimen from the component, mount, grind, and polish the specimen to a mirror finish. Etch with suitable reagents, e.g., nitrile or picrel, to reveal microstructure. Use optical microscopy or scanning electron microscopy, SEM, to examine the microstructure. Microstructural examination or metallography indicators, presence of ferrite-rich, low-carbon zone near the surface, transition zone showing gradual change in microstructure. Microstructural examination or metallography measurement is to measure the thickness of the decarburized layer and compare with acceptable standards. Microstructural examination or metallography limitations is destructive method, requires sample removal. Number 3 of the inspection and monitoring methods for detecting decarburization damage is chemical analysis of carbon content. It is purpose to quantify the reduction in carbon concentration at the surface. Methods: chemical analysis of carbon content to use are microhardness testing coupled with microprobe analysis, laser-induced breakdown spectroscopy or LIBS, welding or spark emission spectroscopy of surface layers, microanalysis via energy dispersive X-ray spectroscopy or EDS in SEM. Chemical analysis of carbon content procedure is to extract small samples or perform in situ analysis, determine the carbon concentration profile from surface inward. Application of chemical analysis of carbon content is to confirm the presence and extent of decarburized zones. Number 4 of the inspection and monitoring methods for detecting decarburization damage is non-destructive testing or NDT methods. These techniques enable detection without damaging the component. Number A, magnetic techniques, magnetic particle testing or MPT, suitable for ferromagnetic steels, detects surface and near-surface cracks or defects associated with decarburization. Limitations: less effective for thin decarburized layers. Number B, ultrasonic testing or UT. Principle of UT is to measures differences in acoustic impedance. Applications of UT is to detects changes in material density or microstructure associated with decarburized zones. Can be used with phased array ultrasonics for detailed imaging. Limitations of UT is resolution depends on the thickness of the zone. Very fine layers may be hard to detect. Number B, eddy current testing. Principle of eddy current testing is to detects variations in electrical conductivity. Applications: eddy current testing is to detect decarburized zones have lower carbon content and altered conductivity, suitable for surface and near-surface detection. Advantages of eddy current testing is rapid and suitable for inline inspection. Number D, magnetic Barkhausen noise or MBN. Principle of magnetic Barkhausen noise, variations in magnetic domain behavior due to microstructural changes. Applications of magnetic Barkhausen noise are sensitive to changes in microstructure and residual stresses related to decarburization, useful for qualitative assessment. Number 5 of the inspection and monitoring methods for detecting decarburization damage is hardness testing. Hardness testing purpose to indirect assessment of decarburization extent. Hardness testing procedure is to perform microhardness or Vickers hardness tests at various depths. Decarburized zones typically show lower hardness compared to unaffected regions. Hardness testing limitations is destructive, requires specimen preparation. Number 6 of the inspection and monitoring methods for detecting decarburization damage is advanced and specialized techniques. These techniques enable detection without damaging the component. Number A, X-ray diffraction or XRD. It can identify phase changes associated with decarburization, such as increased ferrite content. Number B, nuclear magnetic resonance or NMR or neutron diffraction. For in-depth microstructural and compositional analysis, mainly in research settings. Summary: inspection and monitoring methods for detecting decarburization damage. If the inspection and monitoring method in use is visual inspection, is type of non-destructive, the key features of this method is surface discoloration and roughness, the advantages of this method is quick and inexpensive, and the limitation of this method is surface limited and subjective. If the inspection and monitoring method in use is metallography, is type of destructive, the key features of this method is microstructure, decarburized layer depth, the advantages of this method is precise and detailed, and the limitation of this method is destructive and time-consuming. If the inspection and monitoring method in use is chemical analysis, is type of destructive, the key features of this method is carbon content profile, the advantages of this method is quantitative, and the limitation of this method is sample removal required. If the inspection and monitoring method in use is ultrasonic testing, is type of non-destructive, the key features of this method is internal microstructure changes, the advantages of this method is in-depth and non-invasive, and the limitation of this method is resolution limits for thin layers. If the inspection and monitoring method in use is eddy current testing, is type of non-destructive, the key features of this method is surface or near-surface variations, the advantages of this method is fast and suitable for inline, and the limitation of this method is limited depth sensitivity. If the inspection and monitoring method in use is magnetic particle testing, is type of non-destructive, the key features of this method is surface cracks and defects, the advantages of this method is simple and quick, and the limitation of this method is surface only and less effective for thin layers. If the inspection and monitoring method in use is hardness testing, is type of both destructive and non-destructive, the key features of this method is changes in hardness profile, the advantages of this method is correlates microstructure, and the limitation of this method is destructive and localized. If the inspection and monitoring method in use is XRD and/or NMR, is type of advanced, the key features of this method is phase detection, the advantages of this method is detailed, and the limitation of this method is expensive and specialized equipment. Inspection and monitoring conclusion: detecting decarburization damage requires a combination of visual inspection, microstructural analysis, chemical testing, and non-destructive evaluation techniques. Initial detection often begins with visual inspection. Confirmatory and detailed assessment involves metallography, chemical analysis, and advanced NDT methods. Routine monitoring in service can utilize non-destructive methods like eddy current or ultrasonic testing for early detection. Implementing a comprehensive inspection regime ensures timely detection, allowing for appropriate remedial actions such as repassivation, surface treatment, or component replacement to prevent catastrophic failure. Thank you.